what we learn about neutron stars from gravitational wave observations. So in a lot of ways, this is going to be a continuation of sort of the single source inference that we talked about, or that we talked about on Monday this week. But the properties of neutron stars that I'm very much interested in are population properties, namely the dense matter properties in the cores of the neutron stars. So it's going to be sort of an element of that too in how we're going to connect individual observations to joint interpretations. So let me get started here. And so I know there's a lot of folks here that maybe don't have a lot of background in gravitational waves specifically or in the equation of state of neutron stars. So I'm going to give first off a very leading order picture that at least will, and then after I give this, I will tell you all the ways that it is wrong and misleading. It's not wrong, but oversimplified for practical purposes. So let's start off here. So we have neutron stars. They're one of the components in the binary that we're stirring up gravitational waves with somewhere in a distant galaxy. And one of the interesting things about neutron stars is that while we understand the properties of matter in the outer layers, once we get into the central region of the stars, like most of the bulk of the matter of the star, the densities are not densities that are accessible in stable matter form here on Earth. So we get, in our composition here, as we get to the core, a lot of question marks pop up. So it could be that the core is primarily neutrons, like the name of the object, a neutron star. But it could also be that things like hyperons, deconfined quarks start to play a role, that the fundamental degrees of freedom that best characterize the matter in the core of the neutron star aren't neutrons at all. So neutron star here I'm using as a generic term to describe stars with this density above nuclear density at their core where we don't know how matter behaves. So how do we figure out what connects the properties of matter to the observed properties of a particular star? Well, we have an equation of state, which in my field we most often write as a pressure function of density, which has some increasing pressure with density, and then we use that increasing pressure with density to oppose the contracting force of gravity and hydrostatic equilibrium, solve for the relativistic equations of hydrostatic equilibrium, and we figure out, okay, if I start with the central density, I have a star of this mass and this radius from the properties of matter that went into this star. So this, so far, so good. Now for orbital dynamics, when I have two stars orbiting each other, the signature of the matter is not going to be in the radius, it's going to be in the influence of matter on the tidal potential, on the gravitational potential external to the star. Okay, but we can write this down in a simple way. We have our mass of the star, our leading order point particle description, then we have quadrupole correction for the star being deformed, and we can linearly perturb the equations of hydrostatic equilibrium to find out how an external tidal field induces a quadrupole moment with a nice linear proportionality constant, lambda. Okay, very, very beautiful, very elegant. We can write this parameter. It depends, it's a relativistic thing, so this is full GR. But it is a linear perturbation of spherical stars. It's something that's going to go to 0 for black holes in the system. But it's going to tell us how two stars that are orbiting each other influence the gravitational interaction. And that's what's going to imprint on the gravitational wave signal. So we also, of course, we don't only use this to learn about gravitational waves. We can use this to learn about radii. So my equation of state, if I compare for lots of stars, I get radius of stars, I get tidal deformabilities of stars, and I can just calculate the properties of stars. And this is a one-to-one mapping. So if I know the full equation of state curve, I know the full mass radius curve or the full tidal deformability curve, and I can invert that in principle. If I know the full mass radius curve, I can figure out the equation of state. So beautiful. Measure stuff on the right, learn the thing on the left. Okay, so well, how are we going to measure that in gravitational waves? So the key idea is that the presence of tides in the system accelerates the in-spiral. There's extra energy going into deforming the stars. Once they're squishy, they have extra quadrupole moment, and that's what radiates in gravitational waves. So both of these effects mean that as I evolve my system, if I have the radius changing with time from the loss of energy to gravitational waves, well, I'm going to have some extra terms here, some extra deformation, some extra change in energy with radius. Both of those things accelerate the orbit, so I go from whatever my point masses would have done to something where the final orbits are a little bit accelerated. This is a challenging thing to do, actually, to mess up or to affect the binary orbits of two neutron stars going around each other like hundreds to thousands of times per second in the final stages of orbit. This is a massive energy scale. So in a sense, this is a opportunity, so this is pros and cons. So the energy required to change the orbit is large, but this is also a pretty clean signal as far as astrophysical things go. Right? It doesn't matter what the crust of the neutron star is doing. It doesn't matter what the environment is doing. That's not going to have any real significant play on the orbital dynamics of this. We just need this, well, here, this leading order tidal contribution. Okay, don't pay attention to what's going on at the end there. We'll talk about that later. Okay, so now we have an idea of how tides affect our orbits. So we can put that into our model of the waveform that we use to analyze gravitational wave observations. So we have a phase as a function of frequency. So before this, I've gone into the frequency domain. I'm putting a model in that I'm going to convolve with the data. And it's going to be primarily proportional to some time and phase constants, the chirp mass of the system, the frequency term, and then many, many, many more terms. Okay, our gravitational wave models do get complicated, but they have some leading order combos of the parameters that go from how you might think of the characteristics of the system into the things that we can actually measure. So if you look at this as a series of terms, and you package up the terms, and you look at what combinations, order by order, characterize the evolution of the system, I get something that will tell me the chirp mass is the easiest thing to pull out. Then the next correction over that is going to give me some information about the mass ratio and the spin. And then eventually, I'm going to come across a term that folds in the leading order effective tidal contribution, which you can compute in a sort of a Newtonian tidal interaction and put into your model. So these are, they're not the most beautiful combinations. They're getting a little messy here if we're trying to do a full leading order thing. But then we can say, okay, yes, I have some parameters. I compare my gravitational wave data with a model of the waveform that's a function of these parameters, and I recover correlated constraints on what lambda can be, what the mass ratio can be, what the spin can be. And the correlations are important because the assumptions we make are changing the inferences, and most historically notably for 1708-17, the choice to consider the high spin case, where spins were allowed to vary freely over a large range of amplitudes, to a astrophysically constrained limit where we said, well, this high spin is fairly unrealistic if you compare to stars that we know in binaries in our galaxy, and neutron stars and double neutron star binaries. So why don't we just not let the spin go so wild? Let's kind of rein that in, and we'll change, for example, the implication here for the mass ratio towards more of an equal mass system. Now, maybe we would do that the other way around. We'd say, actually, I think neutron stars more often come in equal mass systems, and that would then say that the spin should be low. You can play this game with the tides, too. Well, I don't believe tides exist. It's down to 0, and you get a system that favors extreme mass ratios and very rapid spins. So you're trading between what you assume about these parameters and what you infer. So that's sort of the fundamental thing in these multidimensional parameter descriptions of astrophysical systems. We always have things correlating with each other, and that's going to change what we determine. Okay. So here are some ways that was a very oversimplified picture, and this is why we get away with that simplification. So I don't want to say that picture was wrong. It is an effective idea of what's going on, but it's not the full picture, and it's important to think about where we go next to think about where that breaks down. So first off, the stars, the characteristic interaction in the merging binary that we are actually measuring to make these constraints is absolutely not a linear perturbation of isolated stars. Okay. The P of rho is not one-to-one with M of R for a single observation. So our single observation has one point on, say, the mass radius or the lambda mass curve that we then have to infer the implications for that P of rho function with some sort of modeling of how P of rho can behave. Now, P of rho is not really the equation of state. In nuclear physics, the equation of state of neutron star matter is all the thermodynamic quantities as a function of density, temperature, composition, and from that you get energy, pressure, you do thermodynamic things. In this case here, we are assuming the thing that we're interested in is the cold. That means the thermal pressures are negligible. Zero temperature, which is a good approximation for the stars before they collide. We're assuming that it's in perfect equilibrium at all times, which may not always be true for all parts of the star as the time scale of the merger increases, but is pretty good as far as we can tell. But when we want to compare what we see from observations of neutron stars with, say, nuclear physics calculations or heavy ion collisions, we have to pay attention to what we're actually measuring and where, and what the kind of matter we're comparing it to is and how that's different. So that's sort of, I guess, a repeat here in the fourth point. We want to we want to combine different information from different regimes. So we have to think carefully about how we're mapping between those regimes through the 1D curve onto our gravitational wave prediction. And the stuff that I just talked about on the last slide, what we assume or what we infer about the equation of state is going to be depending on what we assume about the spin, the masses. These are all correlated parameters, and we may want to change what assumptions we make. Okay, so let me talk a little bit more first about the waveform models. Okay, so I mentioned this already, but the deformations of the stars as they're here on the left here approaching each other, they're not linearly perturbed objects. Okay, they're not pure quadrupole deformations. The stars are not effectively described as isolated with an external perturber that's far away, that it just has a linear tidal field kind of thing going on. So why do we get away with only lambda 1 and lambda 2? And when does it stop working? So when does it stop working? Not yet, but potentially soon. So what do we actually use as a waveform model for most of our analyses today? So one technique, and we'll hear, I think, both of these techniques a lot more tomorrow, but for the perspective of how do we put tides into these models, We have two approaches. So one is to build tides in from the ground up in what's called an effective one-body approximation or model for the gravitational interactions. And you can have higher order tidal terms, you can have octupoles, you can have dynamical tides, you can have resonances, you can put in these semi-analytic contributions to the tidal interaction term by term, going much beyond the leading order contribution. The other thing you can do is to build off a binary black hole model where, remember, the lambda parameters were 0, the tidal parameters were 0. Take that as something that you can explore numerically as well as analytically, and add on top of that analytic tidal couplings and numerical relativity fits to the tidal interaction. So by calibrating this with numerical relativity, we're implicitly including all the nonlinear interactions of that full picture that I showed before. So this is not guaranteed to work, right? So this works because of empirical relations that we've observed in the structure of double neutron star interactions. So for example, we can find these empirical so-called universal relations. Neutron stars have lots of these, and that just means that there's tight relations between the different characteristic properties of the star. Depending on what two properties you are comparing, these can be more or less precisely constrained. This, for example, is how you can relate the octupole deformation of the neutron stars to a constant that is proportional to the quadrupole deformation. It's how you can take the F-mode frequency that might play in a role with dynamic tidal excitations at the end of the orbit, fold that into your model, and still have it all as a function of your one parameter. So that's sort of a semi-analytic reason why. And then there's the other reason is that we empirically find through simulations across the parameter space that waveforms from two equation of state models that give equivalent lambda values also give equivalent waveforms. This is a tested relationship. It's not a priori something we could assume to have happened, but it's something that works effectively. So we'll use this essentially when we write our waveform models as functions of lambda 1 and lambda 2. So the numerical simulation community wants to break this because that is a lever arm on new forms of physics. And it's not something that will hold to arbitrarily high accuracy. It's just something that works well enough for the analyses we're doing now. So, okay, so here is some of the points that I wanted to make in terms of how we're going to be understanding the influence of neutron star matter on gravitational wave data. So there's no fundamental obstacle to constructing waveform models that go beyond lambda 1 and lambda 2. It's computationally expensive to explore a generic equation of state space. It's computationally expensive to get your simulations accurate enough to resolve the differences that you would expect to see when you break those relations. And so maybe those are questions for the community moving forward to improve our simulation capabilities. But currently, the models and the parameter sampling that we do, lambda is a descriptive bottleneck. What I mean by that is we take all our equation of state information, funnel it down into these two parameters, and only vary those two parameters when we compare with the data. It doesn't need to be so, and I'll show an example where we go beyond this, but that's sort of what lets us right now actually have some flexibility to decouple our gravitational wave sampling or source properties and inferences for the equation of state. Because you can use different equation of state modeling and just funnel it through those same two tidal parameters and then go back into your choice of waveform models. So you can vary these two sides independently, and they only couple through two parameters, which is pretty manageable to handle. Okay, so another reason why this is fine is that currently we're certainly not getting higher order corrections to the tidal parameters in our measurements. Okay, so our gravitational wave observations are only limiting the leading order combination of the two parameters we're using to describe it. We're not even getting 2 degrees of information out of this. We're only getting 1. So it's not going to be useful in terms of extracting information to add extra complexity to our description. As long as we're well calibrated enough that our description applies to the systems we're modeling. The next largest contributor is the what's called the F mode, the fundamental oscillation mode of each individual star, which gets excited as they approach each other, and the orbital frequency approaches the frequency of the resonance. And so there's some nice work by folks here, Geraint and all, talking about how we can measure that by breaking that description of the waveform to pull out explicitly this next most important descriptor. Okay, so that was sort of one point I wanted to make about where going from the equation of state to the gravitational wave data. I think it's important to realize that there is this sort of descriptive bottleneck there, and that we may want to break that in the future, because that's one of these things that can be easy to assume that that's the way it has to be, and it absolutely does not have to be that way. That's something that we've empirically found to work so far. Okay, but given that we're measuring lambda, what do we actually learn from the equation of state? So there's a few ways that you can say, okay, now I have lambda distributions coming out of my equation of state sampling. What do I infer about the properties of matter? Now, maybe the most basic way to answer that question of what you learned is just to compare proposals for different equations of state to the gravitational wave data, and just do some sort of Bayes factor type comparison to say, okay, this is the most favored, these are the least favored, and perhaps even ruled out, and we can feed in, assumptions about the spin, and see how the resulting different waveform models giving those lambdas produce different rankings, generally the same rankings, but different preferences for the modeled equation of state available in the literature from nuclear theory. Another thing, though, that we actually spend most of our time doing is thinking about functional forms that capture the phenomenology of a generic equation of state. So that could be piecewise polytropes, spectral equations of state, speed of sound frameworks. Those are just 3 of the ones commonly used in the literature today. And so one of the things you do then is you just sample in whatever your equation of state space is, parametrized equations, parametrized spectral equations of state here. You compare for each sample the masses, and then integrate the structure equations to find the tidal deformability, figure out how that tidal deformability generates a waveform compared to the data. So this is generalizable. We could go beyond just lambda 1 and lambda 2 with this framework. We could consider any possible description of the equation of state and go directly to how that is inferred, how the information is inferred about that equation of state. This is also kind of computationally expensive. Right, but we can get some implications. We can generally just say, well, the gravitational wave data, comparing our prior range of sampled equations of state, it's preferring ones that are at lower pressure at around twice nuclear density. You have to support massive stars, so that sort of pushes up the requirement at high density, and you get some posterior range of pressures. So that seems useful, potentially. You can also do this in different ways. So you don't need to do a parameterized formula for the equation of state. Folks have started using stuff like Read and Phil's Gaussian process to generate the equation of state. And that will also give you, from some prior distribution, some posterior constraint on the pressure as a function of density. You can do this with other kinds of observations. So this is results from, I'm sorry, I missed writing the name down and I can't remember it. So you can do this for piecewise polytrope or the speed of sound type prescription for X-ray observations. So this is the nicer data with the new pulsar observation. And you again get constraints of pressure as a function of density. Yeah? Ragemakers, thank you. Yes, that's the one that's the paper that this is from. And then you can also combine the two. So you can do joint inference with the pulsars, the gravitational waves. You get more depending on your modeling for the equation of state function, you get different constraints for pressure as a function of density. Okay, so some computational or let's say representational challenges with this. 90% limits in the pressure as a function of density are what we plot. They do not adequately represent what we're inferring from the data. Okay, so specifically, here's an example of how this happens. Individual equations of state in our samples all support, say, stars of mass 2 solar masses. We need this because we observe stars that massive in our galaxy. The 90% bound lower bound here, does not support that mass. So I can have a line drawn through my 90% contour, which is absolutely excluded by the assumptions that went into this inference. Okay, that's because the pressure inference is correlated between pressures. If I fix the pressure to be on the lower bound at the lower densities, it will have to go higher at the higher bound on the higher densities. Are there other ways to convey this information, I think, is my mathematical question to folks who are thinking a lot about distributions. This is what we plot, but we want to use each other's inferences. So, one way to use each other's inferences to publicly release whatever equation of state samples you're using to generate these plots, and then you at least get a distribution that can answer or that can make sure that this kind of correlated constraint is communicated. But, plenty of people are trying to plot things and compare the plots and make conclusions from that. And is there a better way to do this? So this is sort of my discussion question. Okay. So there are more problems. So not problems, problem opportunities, propertunities. Okay, so the equation of state that we're dealing with. Okay, so we're dealing with neutron stars. We want to compare them to models of the fundamental phase of matter in equilibrium in different conditions. So for example, nuclei here are symmetric between protons and neutrons. So they are symmetric matter. Neutron stars tend to be asymmetric. They have high densities, much higher than 1 times nuclear density. You crash them together, you push up the temperature. That's also the regime of supernova. So we have we're mapping in those pressure versus density plots one line through this, one line through this bottom plane that describes the density that we're looking at for neutron stars and beta equilibrium at each of those densities, but that's not a representation of our full understanding of nuclear matter. And it's not what directly can be compared to observations coming from terrestrial experiments, which tend to use nuclei, which are symmetric and hot when you smash them together. And even how does that compare with implications that might come out of supernova modeling or feed into implications for supernova modeling? So theory-wise, most the most fundamental, or the starting stage for most of the nuclear theory calculations of dense matter, at least that I've seen, start by assuming pure neutron matter. This simplifies the calculations a lot, and you still have, as you go to pressures that go beyond, so nuclear density is around here. As you go beyond nuclear density, your uncertainty bands are increasing. So when we want to map from various neutron matter models to above nuclear density to neutron star models, we typically are going to take some description of the energy expanded around a characteristic density, and we're also going to take a description of how that energy changes with the electron fraction of the stars, the asymmetry, as we move into the space that's representative of neutron stars. So there are many different ways that you can constrain what that symmetry energy is, typically characterized by the symmetry energy at a characteristic density and the slope of that symmetry energy. And we can also kind of work backwards with a flexible equation of state model through to the implications from the symmetry energy picture using modeling or understanding of what the equation of state looks like in a multidimensional way. But this isn't something that you just get for free with that picture. You need to break your one-to-one equation of state mapping to get this to work. So you can, compare, for example, the implied, and people have done this for a long time. This is a paper from 2013. You can compare astrophysical observation to terrestrial observations, but built into this comparison are assumptions about the symmetry energy and how it behaves that come from a mixture of other experimental data and modeling for nuclear physics. So again, people are just plotting things from different groups on top of each other here. But this is a bit of a dangerous game, and I think as a community we can do better to communicate. But aside from just releasing like piles and piles of distributions, is there another way that we can express this information and its correlations? Okay. As we go past the in-spiral, the matter in the merging stars no longer is well approximated by cold, dense matter in beta equilibrium. Okay, we're going to have meaningful temperature. We're going to have changing composition. We'll have other aspects of physics playing a role. So this is going to become more important in future generation observatories as we are able to extend the reach of our observation into the post-merger phase of gravitational waves. Okay. So the final thing that I wanted to mention was that I wanted to propose a discussion on, is how we can best use the inferences from one aspect of the equation of state or the mass distribution of neutron stars to interpret other aspects of that information. So here's an example. So this is 170817's implications for the equation of state using the spectral formulation. So this gives you, so we've had that double peak structure in lambda from the distribution. When you convert that through spectral equations of state to what lambda as a function of mass looks like, you get, again, kind of a double peak-D thing, but also you get the mass the mass dependence characteristic of the spectral formulation. So we can use that, for example, to compare the inferred posterior distribution of the tidal parameters for 1904-25 with a 1708-17 informed equation of state. So really, maybe we want to use this equation of state information as prior. And if we do that, that's going to change the implications for the spin and masses inferred for 1904-25. But that opens a can of worms because not everyone buys all the modeling assumptions that went into the spectral equation of state formulation. So we want to try and be able to do this in a flexible enough way to manage everybody's preferred set of priors. Other ways you can think about this is, I talked about how changing the assumptions about lambda could influence the mass inferences. You can go the other way around too. If I assumed that neutron stars and gravitational waves followed the galactic treble pulsar mass distribution, that would change the way I interpret 1708-17. So, oh, shoot, where did that go? Okay. So, for example, the neutron stars in in potentially emitting systems in our galaxy show masses that have this sort of double peak structure. And that favors for 1708-17 that both components came from this peak. That would make them more equal mass. And that pushes the preferred values of lambda away from the smaller values. But the problem with that is that if you actually observe the galactic neutron star, not the galactic neutron star mass distribution, but the gravitational wave neutron star distribution, we so far do not actually see it following that same distribution. So we have to be careful about applying prior information from other areas of astrophysics because the selection and binary evolutions that carried those stars to merger as gravitational wave sources from the kind of systems that would have emitted as galactic pulsars means that these are two distinct observed populations. So the selection effects and the binary history complicate the interpretation, but there's also kind of this new mass distribution that we're observing in the gravitational waves kind of says, well, where did those high mass things come from? This was already a question for the pulsar observations, as many supernova simulations have a mass distribution that's peaked around the traditionally characteristic 1.4 solar mass neutron star mass. So our gravitational wave observations that show very little peaking, maybe a characteristic power law fall-off, but maybe even a flat distribution of neutron star masses over the values that we consider to be neutron stars. Maybe this is indicating that our understanding of stellar formation is missing something important. And we'll, again, want to connect how we infer that to the description of matter that's going into the supernova simulations and should be self-consistent with what we're inferring about the matter properties of other astrophysical and terrestrial experiments and observations. Okay. And this is all going to become more important in next generation. So here's an example of the fidelity on the individual component lambdas of a star that would be expected for a double neutron star merger in a next generation observatory. So this is GW200105 and you can see from the tightness of the constraint on the joint combo of lambda 1 and lambda 2 that this is probably going to break a lot of the things that I'm worried about breaking, which is great because this is an opportunity to learn new physics. So here's the end of my talk, and these are the questions that I would be interested in discussing more. So specifically, how do we communicate the results we get from gravitational wave inference effectively to people that are studying the properties of matter in other fields? And especially, how do we package up the prior assumptions that we're putting into things? How do we allow people to combine things to make joint constraints? Do we just keep releasing piles of equation of state samples and just chug through the computational power of that? Or is there another way that we can better communicate our results in sort of a headline way that's more manageable for people to use. Also, how can we explore different possible prior assumptions we might be interested in developing the implications of in a flexible way, and let people choose the information they want to use? Because our community would be interested in saying, like, well, maybe some folks are worried about systematic uncertainties in the NICER pulsar observation. I don't want to use that in my prior equation of state inference, but other folks might be like, I actually really buy into that measurement. That's the one I'm going to take as my full-on confident prior information, and I want to see how that propagates to other observations. The propagation is all density cross-correlated and parameter correlated, so this is something that do we just need to keep, as I said repeatedly, putting out equation of state distributions? And how do we ensure that the level of information we produce for our distributions allows for this kind of post hoc modification? And I'll stop there and ask for your questions.